Okay. So I've moved. So I've had to adjust our schedule a bit in terms of what we're doing over the next couple days because I want to make sure that we can do proposal day on the 4th. So we will be going over Monte Carlo stuff this week, starting immediately, and then we will, ideally I would have wanted to get the exam on the 5th, but that's just not realistic, I don't think, with the amount of stuff. So the exam will most likely take place on the 12th, 15th, depending on your thing. It's much later than I would like, but that's just the way it's got to be, unfortunately. 12th, 15th. Okay, with that, we're gonna get started. So we'll go over Monte Carlo stuff. Then I'll I'll go over some project stuff on Thursday while covering more Monte Carlo stuff, giving you the chance to start brainstorming. So start thinking about like who you want to partner with for your final project. Start brainstorming ideas. But we'll talk more about like the different kind of projects you can do on Thursday. And the idea here is that I want you to try to have we'll try to have something of an idea of a project what to do next Thursday. Not this Thursday, but the Thursday of next week. That should be a good day for doing, figuring out what a project is. That's my goal. If I have to shift it, it happens, but I really also want to make sure that you have plenty of time to like execute that final project. And I feel that like doing it then gives you the entire rest of the month to open for the final project. There are no other homeworks besides Pig, by the way, with the final project. Yes?
Is there a maximum amount of people?
3. There's the maximum amount in a group is 3. More than that, you've got people who won't pull their weight evenly. 3 is already more. At 4, you've basically got people who it's harder to basically split up defined tasks. But your group can be 1 to 3 people. You do not have to work in a group. You can work by yourself. You can work in pair with one other person. You can work with 2 other people. I've never approved a group of 4 people. I just don't. It's not gonna. If you've got 4 people who want to work together, split up into two twos. Sorry. Okay. All right, let's go ahead and get started with this. So we're gonna play a game, or let's suppose I have a game. Suppose I've got a game, and I say let's play a game for money. Okay, we're not actually gonna play for money, because law of large numbers said I'd probably be investigated for unethical behavior at that point. Because this is the game we're going to play. I've got 5 red cards and 2 black cards. Just like standard playing cards, I've just simply color-coded them for visual sake. Okay? And what we'll do is that I will shuffle them up. Okay? I can shuffle them. I can like move them around here, change the order of them, shuffle them up. And then I can just move it to my other screen over here. And then keep my mouse over here so there's no shenanigans. Right? And so what is the object of the game? The object of the game is that you need to choose 3 cards. Specifically, what we need to do is I want you to choose 3 red cards without choosing a single black card. Okay? So card 1, 2, 3, 4, 5, 6, 7, right? 7 cards, 1, 2, 3, 4, 5, 6, 7. You win if you choose 3 red cards. And you lose but you lose if you draw a single black card. Okay? Make sense? Okay. Now what we want to find out though is what are the odds of winning this game? After all, let's see what we've got here. We've got let's just think about this for a second. Your first card, when you draw it, that's a 5 out of 7 chance of winning, right? Of getting a red card. After that, there's 6 cards left, right? So your second one, your chance of success of drawing a good card is 4 out of 6, and your third card is 3 out of 5. all those numbers are above 50%, right? Those are all better than those are all better than average chances of drawing a card. So you're not at a disadvantage for this game, right? Well, let's go ahead and play this. So I'm going to go ahead and move this down. I'm going to expand this screen. Hold on one second. And now I'm going to move the cards around so that you won't know where they are. All right. And now, okay. And now we'll choose some cards. Who wants to go ahead and choose a card? Choose a number 1 through 7. And let me... 7. 7's good. Okay. We've chosen 7. Let's choose... We need to choose 2 more. Yes. 2. 2's good. 1 more card. 3. 3 is good as well. So this was the configuration for that one. So you won that one. Let's go ahead and try this again. All right. So who wants to choose one now?
1.
1 is good. 5. 5 is bad. All right. Let's one more time. I'll shuffle this up. Okay. All right. I've shuffled it up again. 4 is good. 6 is good. Yes. 7 is good. Yeah, I mean, you did pretty well on this. 1 twice. Now, so what do you think the odds of winning this game is? Anyone? I mean, obviously you won 2 out of 3 times, so the odds must be good, right? No? That's the issue with small sample sizes. They can lead you into a false sense of security. Because I lied to you here. I said your chances of drawing your first card. I mean, I didn't lie about this part. I said your chance of drawing a card that is 5 out of 7, right? You know, a good card, it's 5 out of 7. That's just logic, right? Second card, same, it's 4 out of 6. And the third card, there's 3 red cards left, 2 black cards. So there's 3 out of 5 chance of drawing a third good card, right? Those are all better than 50% chances. Not a lie there. So the lie I told was, so your odds overall must be around 50% or some such. That is not the case, because these are not independent odds. These are dependent odds, which you don't know about yet because you haven't taken probability and statistics. If things are dependent on each other, what do you do? To figure out if odds are dependent on each other, what do? You have to multiply them. So the odds for winning the entire game is 5/7 times 4/6 times 3/5. So let's just go ahead and pull out the calculator for a second. 5 times 4 times 3 is 60 over, okay, 7 times 6 times 5. 60 over 210. Or we can simplify this to 6 out of 21, and we can further simplify that by dividing by 3 to 2 out of 7 is your chances of actually winning. 2 out of 7 are the chances of winning. The point of a lot of games like this is that they need to seem fair on the outset, and they need to have a convincing story. But the truth is that I wouldn't challenge a person to play a game of money if there was an even chance of me winning. If I'm challenging a game for gambling and I want to make money off of it, I'd rig the game. And that's exactly what this kind of game is. It's rigged. There's another variation we'll look at later today where it's a grid of cards. I believe, what is it? I think it's 2 cards and 9 cards, and it's still bad game. We've got a grid and it's lined up, and you got to get 3 in a row. Okay, without getting a red card. These things are. So the question then becomes, wait, this isn't a statistics class. So what should I do if I don't know to multiply dependent variables together? What do I do if I don't know how to, what do I do if I don't know how to play this game, if I don't know how to figure out the odds? And that's where this week's lesson comes in, which is probably which is like the last kind of formal unit I have for you, which is Monte Carlo approximations. So and here I'm just simply I'm pulling up a private window so I can go to Google Maps without showing any of my personal data. So here, right? Let's go. So first off, Monte Carlo method sounds like a big, complicated word, and of course, if you go to Wikipedia, it's probably intimidating. Monte Carlo. Monte Carlo is in Monaco. I'm not sure how to say it. Okay, Monaco is one of those micronations. Specifically, it's between France and Italy. Right? If we zoom out, it doesn't even really appear on the map all that much. Right? It's by Nice. You can see it right here. It's its own independent nation. Right? It's a country. But it's really tiny. And Monte Carlo specifically is a small area in that city country thing, this micro country, specifically devoted around the Monte Carlo casino. As I mentioned, I believe I mentioned a few lectures ago that basically much of the beginning research in probability and statistics came from gambling. And this is true for Monte Carlo as well. And the idea here is that there's a bunch of different games, might be roulette, baccarat, or blackjack. And these are games that have a high roulette, fairly straightforward in looking at. But what about a game like craps or baccarat or blackjack? Games that depend on human decisions. How do you even figure out what the odds are without getting into this giant decision tree and having to just do a lot of calculations? And the idea behind a Monte Carlo approximation is that if you want to figure out the odds of a gambling game and figuring out what your odds are winning, watch the game get played and then count the number of wins versus the number of losses. And if you watch enough games, that will get actually close to the real value of the game, right? We'll be able to figure out what the real value of the game is. For context, and by the way, for anybody who is actually interested in gambling, when it comes to casinos, does anybody know what the game that has the smallest house edge on it? Basically, the game that is most fair towards, most tilted towards the player. Blackjack. Blackjack is the one with the smallest house odds. Assuming you're just playing with, if you're following basically a table to play perfectly, and suddenly you don't have to make any decisions, the house's odds are less than 1% at that point. But the house always relies off of the law of large numbers to make money. That's how it works. Just they have to have enough people playing enough games. They also have specific limits to avoid certain betting strategies that could that allow a player to make up their losses, to keep people with lots of money coming in and actually making money from going to the casino. There are betting strategies give enough money and no limits to the betting that you can actually. Assuming you have an unlimited amount of money, you can always win at a casino by following a certain strategy. And with different games, because eventually you'll hit a streak of wins. Eventually, because if you have unlimited money, you'll never run out of money. that being said, most people don't have unlimited amount of monies to play around with that. So now, on the other hand, blackjack, if you do in fact happen to count cards, which is not illegal, if you count cards, then the edge suddenly goes towards the player. Of course, it's not illegal, but the casino can then politely ask you to leave, or impolitely ask you to leave, or they can just send somebody over to distract you, or possibly spill a drink on you. Accidentally, of course. But the point being is that, like, if they suspect you counting of cards, they have various ways to do that that don't involve necessarily, trying to call the cops, or they can, it's just really dependent on it. So, now let's go ahead and, now that we've talked about gambling, let's actually look at the odds for this particular game, right? So let's open up Idle to figure this out. Okay, that's what we're going to do today. We're going to figure out the odds to this game, and then we're going to figure out odds to other games, as well as and we'll also look at a project in our book. So to win this, so the only thing we really need to know about statistics is that choosing that with this game in particular, like where we're just choosing cards at random, it doesn't really matter which cards we choose. Choosing 3 random cards versus choosing always choosing cards 1, 2, and 3, that has no difference, right? If you play enough games, it will statistically be the same. So the way that this Monte Carlo approximation works is that it always kind of follows the same kind of format for doing this. Okay, which is so. Okay, the first is because we're dealing with having to choose things at random and or we're dealing with things that are configured at random, we will need to import random. This is probably where we're going to use random the most. Okay? Okay. The next thing we do, once we import random, is that we are going to define a game. Okay, and it's either going to return true or false. And I'll just simply leave it empty to show you the format of all the Monte Carlo. Basically, whenever you do a Monte Carlo approximation, it kind of looks like this. Import random, game, return true. Some games we might end up instead of returning true or false, might end up returning a score, in which case you just simply keep a dictionary. I'll show you how to do that in a bit with this problem. And then we just simply do something like this. Trials is equal to, let's say, 10,000. It can be 10,000, could be 100,000. I find that's a good amount to figure out. That's a statistically significant amount. And we say for in range trials, basically we do a for loop. Basically what we want to do is we want to play the game, 1,000 times. Okay? If game equals true, right? If the game was true, we actually don't need the dot equals true, the double equals true, but I find a lot of students find this much easier to understand. If we get true back, that means we won the game. And in that case, what I'll do is I'll keep a count of wins. It's equal to 0. If game is equal to true, wins plus equals to 0. Because winning and losing is a binary choice, a binary thing, I'm not going to bother even keeping track of the losses, because you can just figure out losses by saying trials minus wins, right? So if game is equal to true, wins plus 0. And then that's basically it. We print out the number of wins divided by the number of trials, the number of games we've played, and that's it. This is all, by the way, remember, I make this all caps out of habit to basically say this is a variable that we don't want to change, that basically once I've set it up, I don't want to change what its value is in code. I only want to ever use it. And this is so that if I want to change the number of games I'm playing, I only have to change it here in one place. I don't have to change it. The reason I have a variable is I don't have to change. If I change it from 10,000 to 100,000, I don't have to change it in two places. Because if I have to change it in two places, that opens me up to forgetting. And I'm a very forgetful person. Okay. So now let's go ahead and make the game. Right? Our game involves having, let's go ahead and say our cards are equal to, we have 2 black cards and 5 red cards. So I could simply define that as B, comma, B, right, comma, red, and so on and so forth. I'm actually going to be lazy here and remind you of a trick that I can do. I've got black cards and I've got red cards, right? I'm going to go, oh, and yes, I need to put them in quotation marks. And I have 2 black cards, 5 red cards, right? This statement says make 5 copies of this list, or this one says make a list with 2 copies of this. And then I can concatenate them together. It works. It just works, right? Let's go ahead and comment. I'm going to comment out this part for right now, so I can just simply call game and show you what I mean. Print cards. Okay, print cards. No, print game. I don't need a print game. I'm just calling it. Sorry. That's what I get when I talk and type at the same time. So here, right, you can see that it came out with black, black, red, red, red. 2 blacks, 5 reds. The next thing we're going to do with random is that there's a lot of nice built-in functions with random over here. Specifically, what we can do with this is that we can we can do shuffle. That's one of my favorite functions over here, and it's one that for this kind of thing we'll use a lot. Random.shuffle cards, and you'll see from our output, we run it, that was it 5 reds and 2 black cards? I always forget. Let's see. Did I use? Yeah, I used black. I used what? I used black cards as the losing card, right? As the card you draw when you lose. It really depends. I think last year I used the red cards as the losing card. Okay, so if I draw a red, I lose. It's the reverse of what I did, but I don't want to change it now. It'd be too confusing. So here you can see that the black cards get randomly distributed, right? And so do the red cards. Red, black, red, black, red, red, red. Okay? So this works at shuffling it up. It's great. So now that I've shuffled it, we need to draw the cards. For the sake of simplicity and for speed, I'm just going to choose my the first 3 cards. My picks are equal to cards 0 through 3, right? That's the first 3 cards. Index 1, index 2, and index 3, right? Slicing is super useful in Python, right? I could randomly pick 3 numbers, right? And repick it if it's one I've already drawn, but it's going to be the same statistically as whether I draw 3 at random versus just simply choosing the first 3. If B not in picks, so if I did not draw a black card, I won. Otherwise, else, return false. So if I didn't draw a black card, I win, right? I needed to draw 3 red cards to win. Otherwise, I drew a black card. I lost. This can actually be further simplified, by the way, this code. Again, the more you program, the more you realize you can simplify things. Because if this statement is true, I return true, and if it's false, I return false. I can just simply return this statement. If B not in pics. Does that make sense? And so let's go ahead and try it. Return B not in pics. So it's amazing how short you can make things in Python. I love it. So I run it, and there we go. 0.2815 is our chance of winning the game according to this. We can run it again, and we'll see that because it's random, we will get slightly different results. 0.2898. 0.27, sorry, so 27%, 27.93% chance of winning. 28%, 0.7% chance of winning. The more trials you do, though, if I do 10 times more trials, it's going to take 10 times as long to calculate, but it adds another digit of certainty. 28.5%, 28.2%, 28.2%. So the range of what it's doing is lower. But basically, you can say, no, this is not good odds. And you don't have to know anything about statistics to figure that out. You just simply say, this is the game, we play the game, we're done. So there will be a Monte Carlo question on the second exam. Okay? On the in the practice exam, which I'll send out soon, I've given basically. So the question I asked on an actual exam, first time I did this, and I thought was such a good question that I went ahead and spoiled it for everybody, and it's now a permanent practice question. So this is a real question that I asked on the exam. Here's a game of Monopoly. What are your chances of rolling yourself into jail? What do I mean by that? I explained the rules of Monopoly, but what that means is that in Monopoly you have two six-sided dice, 2d6 for those of you who play D&D or other games like that. So you have two six-sided dice, and the way it works in Monopoly is that if you roll the two six-sided die and they end up on the same number, so you roll two fives, you get a roll again. And if you do that again, you get a roll again. But it basically gives you an extra turn. But if you roll, let's call them doubles, where you get the same result on both dice 3 times in a row, you go directly to jail for speeding, as it puts in the game. So check the actual rules for Monopoly. Monopoly is actually a brutally short game, or can be a brutally short game if you actually play by the rules. Anything that adds money into a pot, like with the free parking space that a lot of people do, that just extends the game further than it should. Monopoly is meant to basically get a person who runs away very quickly. So with regards to that, that's a question I've asked, and you'll see so that's a game we've done. Another game on that might be of similar. Let's see. A game like this might be something I ask on the exam as well. Basically, where you just have to where you have to lay out the game. The final games that I've used for the past couple of years on the final exam, it does involve a decent amount of code, but the rules are not complicated. How do I know they're not complicated? Because the game is literally made for kids under 3. That is how I know the game is not complicated. It's literally made for kids under 3 to teach them how to take turns. It is a very easy game, very easy to understand rules, fairly straightforward to simulate with one kind of, we have to pretend to make that children of that age will make optimal choices. But aside from that, it's a very straightforward game that I've been using the couple years on the final. That being said, I'm going to have to redo how I do the final exam this year, because what I've done in the past couple of years is with it being on Canvas is that it's not going to be on Canvas, it's going to be on paper. In the past couple of years, what I've done is that there's 7 questions worth 20 points. You choose 5 of them, so you get to choose which 5 questions. So it'll probably be something along those lines for the final exam this time around, or it will be this time around, something maybe more along the lines of, here's 4 short questions and then 5 big questions. The short questions are each worth 10 points. The big questions are each worth 20 points. Here's 5 big questions. Choose 3 out of the 5. Okay? Basically, here's questions. Choose the ones you're most comfortable with. Okay. Which, depending on the person, might be there. So this is, again, a fairly straightforward game. Some games, though, but like it looked like it was a fair game at the first glance, but there's a few others that are, not. Good. Let's see. That was just. So let's go ahead and go to our. Let's go ahead and pull up our runestone exercise for the day, because while runestone does not have a chapter on Monte Carlo approximations, but it does have a project page on it. So we'll go ahead and go to that. So you can either go directly to Runestone and look for them and go down to the projects and look at the Monte Carlo stuff, or you can do what I'm doing, which is go to the modules. Go to week 9, Monte Carlo approximations and cheating at statistics, because that's what this is. We are just simply saying math is hard. I don't like math. I don't want to do the math. I'm lazy. Let's instead just not do it and instead just count how many times I win. Okay. So click on that one on the bottom, and that should bring us to Spring 2024 Rosen. And we'll do parts 1 and 3, but what we're going to do is we're going to skip part 3 for right now. Sorry, part 1 for right now. And we'll scroll down to over here where it says the Monty Hall Challenge. So this is an extremely famous question. If you were in Dominique's Professor Kleiger's class on Friday, you may have seen me go over this one, but it is extremely famous. It's called the Monty Hall, and it's not. The fact that we're going to be doing a Monte Carlo approximation on the Monty Hall problem is completely coincidental in terms of the naming. It's famous. The game goes like this, okay? And there used to be a video here. There is usually generally one. Okay, so the way it works is that the game typically works, or the way the game is presented, is that we have 3 doors. Okay? 3 doors with a hidden prize behind each of them. Okay? Behind 2 of these doors, okay, Monty has placed a goat, represented by the letter G, and behind one of the other doors, he's placed a car, represented by the letter C, right? Monty knows where he's placed them because it's his game. He knows he knows that door number 1 in this case has the goat, door number 3 has the goat, and door number 2 has the car. Okay. And also, very important here, we're assuming that the car is more valuable than the goat, right? The car is the desirable prize, and the goat is the undesirable prize. So, as opposed to, oh, come on. Why am I having so much trouble with this? Why am I having so much trouble getting between stuff? Monty Hall XKCD. As opposed to, my wife would be this person, who'd be happy with who'd be very happy with the goat. So for the sake of argument, we have to assume that we want the car. All right? So the way the game works is that you, the player, choose one of these 3 doors, right? Okay? So let's assume for the sake of argument that you choose door number 3, okay? Okay. Let's go ahead and actually give us some blank doors, because that way we aren't biased by what we see. So 1, 2, and 3 are our doors. So we have 3 doors, and we suppose we choose door number 3 as our choice. Okay. So that's first step. The second step is that Monte will then reveal a goat. He will open up a door. Let's say in this case he opens up door number 2. Okay. Door number 2 to reveal that there was a goat behind that. Because he'll always open up a door and reveal that there's a goat. That kind of increases the pressure of the game. Makes things more dramatic. Okay? Plus it'd be boring if we revealed the car because of the next part of the game. It would give no meaning to the next part of the game, which is that he asks you the question. Do you want to switch? Do you want to switch your choice? That's the kicker. That's what makes the problem interesting. And so the question we need to answer is it better to switch or not to switch? And if so, what are the odds of that particular strategy? Okay? Now, what do people think? People who haven't seen this problem before, what do you think? So who hasn't seen this problem before today? Anyone? Well, some people, right? Yeah, a lot of people. Okay, just people being shy. So, like, on your first instinct, not necessarily after you thought about it for a second, on your first instinct, what do you think the odds are if you switch? Okay? Because don't worry, you're going to be, if this is your first time seeing this problem, you're going to be wrong about the odds. So don't be afraid to be wrong. You're going to be wrong. Anyone? Yes.
I would think that you're supposed to be thinking you're getting a 33% chance with each door, but I would think that it's probably less, and you'd be better off sticking with the door you originally chose.
Because you think I'm a trickster, right?
Yeah.
Yep, that's very good logic to think that to try to. That's a very good instinct, by the way, to mistrust the person playing the game. The logic that most people think of is what? That there's now 2 doors, so now it's a 50-50 shot, right? That's the instinct that most people think of, which is also wrong. It's not, I mean, yes, if it was a 50-50 shot, your initial odds of not switching would, you went with a 1-3 chance. In switching, suddenly it's a 50-50 shot, right? You switch or you don't switch. So here's the kick. So this is what makes this problem so confusing and confounding for a lot of people. This is why it's listed as a paradoxical problem, even though it's not paradoxical. It appears to be. The odds of winning if you switch are actually 66%. 2 out of 3 if you switch. This is kind of funny. Really, so if we look at so for instance, we look at the Monte Hall problem. Just to go over here to the Monte Hall problem on Wikipedia, it's got its own page with his own drawing of a goat and a door. Right? Look at that adorable SVG goat. Right? Scalable vector graphics. All right, so. This got asked. This became famous when it was asked in Parade magazine's column for Marilyn Vosavant, who's a very, very intelligent woman. They asked basically the question the way I phrased it. Do you switch? Is it in your advantage to switch? And Vosavant wrote correctly that you should switch under the assumptions that you've given me. There's a 2/3 chance of winning the car. And the important thing here is that the assumption is that when Monte reveals a door, he's always revealing the other, a goat or the other goat if you landed on a goat initially. Okay. So, and what this is that it is. So yeah, when the player makes their choice, there's a 2/3 chance that that basically you made a bad choice. You didn't choose the car. The probability does not change until you reveal goat. When that information is provided about the 2 unchosen doors, that now swaps. This is due to some stuff in statistics due to Bayes' theorem. But honestly, it feels paradoxical. It feels like it should be half and half. And you're not alone. Many readers of Vosavant's column refuse to believe that switching is beneficial and reject your explanation. After the problem appeared in Parade magazine, about 10,000 readers, nearly 1,000 with PhDs, although I don't know how many had math PhDs, wrote to the magazine, most of them calling her wrong. Even when giving explanation simulations, formal mathematical proofs, many people did not believe that switching is the best strategy. It's one of those things that is really hard to, for people. So we're going to do that simulation instead, right? I'm not going to bother trying to go through like the statistics and using Bayes' theorem, using conditional probability. Instead, we're going to just figure it out by simulation. However, before I do that, let me go ahead and just I find that the explanation ad absurdum works best. Basically, let's simulate this problem to a level of the absurdity. Suppose I've got instead 1,000 doors with 999 goats and 1 car. Okay? Pick a door, any door. Okay, I pick door 1,000. Monty then opens up 998 other doors, revealing a bunch of goats. And then he asks you, do you want to switch? I mean, yeah, of course. Because my initial guess was 1 in 1,000. And now it's not 1 in 1,000. It's significantly better than half because I'm now betting that because what's the bet now? My bet is not, did I choose the right door? My bet is, did I initially choose the right door? Did I originally choose the wrong door? And that was a 1 in 1,000 thing. It's a 1 in 1,000 chance that I initially chose the wrong door. So now I have the chance to kind of play the odds, right? That's what That's what we're doing here. He is revealing all the doors that don't have goats in them. All the doors that don't have cars in them and that you haven't chosen. So, right, that I feel like if that doesn't help with explain the math, it certainly helps explain, okay, that's why I should switch. Because that additional because you just simply can show that basically your odds slowly go down as we get less and less doors. Okay, so let's go ahead and simulate this, right? So same thing, what we'll do is that we will, we can do import random. Okay? And we can just simulate this. Def game. Right? What we'll do is that we'll simulate this game with the switching strategy. Right? We've got our doors here. We've got a goat. Yeah, let's go ahead and blow this up. Goat, another goat, and a car. And then I'm going to shuffle them up. Random dot shuffle. Doors. Okay. Now once again, I could simulate this just by saying we always choose door number 1, index 0 in this case, and we always switch. Right? And that leads to just kind of a boring but let's go ahead and actually simulate what basically the choice. Okay. Let's see. Let me just I just need to go to Python for a second and remind myself. Random dot rand int 1 to 0 to 2. Let me just see if that's the one I want. It's either random int or rand range. I think it's rand int. Yep, it's rand int. Okay. Random.rand int, and rand int this generates a number inclusive, 0, 1, or 2. Right? Generates a number inclusive. Random.rand range will generate a number exclusive. This would only generate the numbers 0 and 1. So this is the only time where the endpoint is actually inclusive in programming. Got it? Okay. And if you forget that on a test, oh well. Oops, that's going to be a 1-point mistake on a test, right? That's one of the minor things. It's one of the easy things to debug. But it's one of those things that you wouldn't make, mistakes you wouldn't make if you had the documentation. Okay, so let's go ahead and say that the pick is equal to this. Okay, logic. If pick equals 0, right? Pass. If pick, or not if, but elif, pick equals 1, pass. If pick, well, no, there's no elif there. There's just an else. If it's not 0 or 1, he chose door 2, right? Okay, and we'll put pass there as well. So pick 0. So let's say that he picked 0. Okay. So Monty and thus us knows this information. If doors pick equals a goat, right? If the door is equal to a goat, then Monty will basically reveal the other one. He'll open up the other door, right? And then we'd switch and we win the car and we'd win. So honestly, it doesn't matter what we pick. It really doesn't. Basically, it's just simply asking if pick. I'm going to just short circuit the logic here. Return. Actually, no, I need to work through the logic for you. Let's go ahead. Pick is equal, if door is equal to, so if doors pick is equal to a goat, then Monty will open up another goat and will return a car. I'll do return car rather than return, Monty reveals the other door. He has no choice but to reveal the other door, right? The other goat. And then I switch and I get to the car. Otherwise, if I chose a car initially, he'll reveal the goat, a goat, and I'll switch away from my car to the other goat. Right? Make sense to everybody? And honestly, I can just simply, it's the same thing if you choose door number 2 or door number 3. Make sense? That's why I said I could just short circuit the logic, right? Well, it doesn't really matter now. I can simplify this later. Let's go ahead and just simply run this program. So trials is equal to 100,000 is equal to 10,000. For in trials, okay. For blank in trials, none for if the game result of the game is equal to a car, wins plus equals 1. Or not wins plus equals 1. This one is wins equals 0, and then here wins plus equals 1. Again, what happens when I type and talk at the same time? Okay, and the next thing we do is is that we just simply print out our result. Print wins divide by trials. Okay, and don't worry, I'll share this code with you. I'm actually going to go ahead and run it, share it right now so that you have access to it. Okay. Oh, int is not iterable on line 26. So hold on a second. For blank in very common mistake I make, very common mistake you make as well, I'm sure, as you're coding. But again, it's one of those. The thing about mistakes is like, I've noticed, the more you make them, it doesn't necessarily mean you stop making them. It just means that you just kind of know how to fix them. Like I knew I forgot the range this time. And now it says my chances of winning are 66%, which is kind of what I said. So now I'll share the code there. Didn't actually give me a confirmation that it's shared, which is annoying. Okay. I don't think it hit. Oh well. Give me a second. Do. Okay. Okay. Do. Carlo. Okay, and then I can also grab this other code from here. And then there's one other piece of code, though, that we will probably want to go over and include in here. Okay. And that is, so this is pretty cool. I personally think, being able to figure out games like this. And in case you're curious as like to where you could go with a final project on this one, if you're interested in trying to predict stock prices or possibly crypto prices or prices of any commodity, you can use Monte Carlo. It's very common to look at doing Monte Carlo simulations to predict the prices of a stock, right? And then you can use that to kind of look at the daily changes and then figure out what the average change is, and then, and then use random functions in there. Once you figure out the average, so you take data, figure out what the mean and standard deviation is, and then use that Python do all the heavy statistical listing to generate random numbers to kind of figure out where what the next couple days might look like. It's really how it works, at least on the basic level. Okay. All right. Now this one I'll go quick over because I've already written the code for it because I wanted to show my kids something cool for Pi Day. So as you can go, we went. So do you remember this Leibniz formula from the beginning of the semester? It was a while ago. Approximating pi by doing pi over 4 is equal to 1 minus a third plus a fifth minus a seventh plus a ninth, right? So we did that. And we basically were trying to approximate pi over 4, and then we multiplied the result to get pi. So that's kind of fun. Python can do that, but there's a different way we can kind of look at this problem. And this is like the classic kind of Monte Carlo approximation that's not, so to speak, a game. Okay? So, and it works like this. Okay, suppose we have this dartboard. Sorry, we have a, suppose we have, yeah, that's close enough. Suppose we have this dartboard inside this square. Okay, and let's go ahead and let's assume that's a square and not a rectangle, right? All right, and furthermore, that this is, for this, we will assume that this is the, so basically, this is the way, so suppose we have this dartboard, and we can throw a dart, and I've got this magical gravitational field in this square around it. So I can't throw a dart, and what it means is that I can't throw a dart out here. Any dart I throw is going to land in the square somewhere, right? It might land in the dartboard, it might not land. But basically I've got this field over here to make sure that nothing lands outside of the dartboard. Make sense? Okay. Now, we can, believe it or not, use this to calculate pi over calculate pi by looking at the ratio of the number of hits that land inside the dartboard versus the number that doesn't. Why? What does this give us? So for the sake of simplicity, we're going to look at this as though it's the unit circle. What do I mean by that? It's a circle with what? Radius, what? 1, right? So let's suppose this has, and this actually gives us quite a bit of information just by writing down that the circle has a radius of 1. For instance, now we know how big is the side of a square then, right? 2, right? So this is a unit circle and its sides are touching the square. So the circle's diameter is 2. So the side of a circle is 2. And that means that the area of the total area of the so what is the total area of the square? Right? Not a trick question. What's the total area? How do we figure out the area of a square? Sorry? It's 4, right? We just simply square, we do the side length squared, so 2 times 2, which becomes 4. So the area of the square a square is 4. All right, the area of the square is 4. What's the area of the circle? So remember, the radius over here is 1. What's the let me rephrase this. What's the formula for the area of a circle? Pi r squared. Pi r squared. All right, let's plug it in. What's 1 squared? 1 squared is 1. Oh, that's appropriate, even though I didn't totally mean to do that. Okay, 1 squared is 1, which means that the total area of the circle is just pi, right? So the ratio of the circle's area to the square's area is pi over 4. Make sense? The area of the square is 4. The area of the circle is pi. Everybody following so far? Right? Did I lose anybody? Right? This just simply comes from the fact that the radius is 1, the diameter 2, and the side is equal to the diameter. Okay? Those are just givens of the problem. And I've defined it by this I've defined it like this for simplicity's sake because it becomes so much easier to do it like that. So now let's go ahead and assume that we've got this. Now that we've established that, we have this, again, magical dartboard that basically if I throw it, it's going to land somewhere in the square around it. Okay? And we want to count the number of hits that land in the circle over the total number that land outside of it. And what we should expect to see is that the ratio of hits to of hits, not to misses, hits to total number of throws well, that's going to be equal to the number that the first number is the number that lands in the circle, and the second number, the number of throws, is just the total number we throw, which is going to be the number that land in the square. And all the stuff that lands in the circle lands in the square, right? Because the circle's inside the square. It's going to approach pi over 4. Does that make sense? So how do I simulate this? Okay. Well, it's no fun to just do it mathematically. I'm going to do it visually instead, of course, by using Turtle. So let's go ahead and just kind of show you, before I go into the rest of the code, here is the code for tossing. Okay, So to toss a dart from the range 0 to 1, here's another random function, right? And if you don't know them, it's fine. I mean, again, rand int for the sake of the exam, any exam I give you, there's really going to be only 2 that you should know. Okay? There's 3 random functions you should know. You really only need 2, but you should know 3. The 2 you need to know are shuffle, right? Obvious reasons that's a good one to know because it shuffles everything up. The other one is rand int, which chooses a random number, right? And you can use that to simulate the last one, which is choice, because you could always use rand int to give you an index. Choice is great because it randomly chooses something from a list. Okay, we might see it later, we might not, depending on what we need. But rand int and shuffle is pretty much all you need. This is especially important because we will be able to use this for dice rolling, right? Generate a number 1 through 6 for a 6-sided die, or coin flip, right? Generate a random number 1 or 2. So this one, uniform, is one of the more esoteric ones, but still very useful. It's generating a number from -1 to 1. But but when I say number in this case, I don't mean integer. I mean real number. It generates a real number between, it generates a float between -1 and 1. Similar over here. It generates an x value, a random x value and a random y value that's going to be between 1 and -1. Okay. What we'll do is that we will define the center of this circle over here as the origin. Okay. So that center of the circle, that is 0, 0. Make sense? This is 0, 0. This corner is -1, -1. This corner is +1, +1. Make sense? This is just simply the coordinate. So I'm defining a coordinate plane, right, on this. Just a very small, but I'm only really focused on that small portion between the negatives, -1, -1, and +1, +1. Make sense? And this, in case you're curious, right, is 1, -1. So we're generating a random number between -1 and 1 to figure out where our dart is landing. It could land here, it could land here, it could land here, it could land here, it could land here. How do I know it lands inside a circle, though? Okay, well, first off, given that the radius is 1, a circle is defined by basically its radius. That's all it's defined about. If a throw is within a radius distance from the center, it's in the circle. If it's beyond a radius distance, right? It's outside the circumference, in which case it's outside the circle. So anything where the distance from the center is smaller than the radius, it's a hit. And if it's bigger than the radius, it's a miss. Now the radius is, as I mentioned before, it's just 1. So this is the only annoying bit of math, which is how do we figure out what the distance of a particular throw is from the center? What is the distance from that throw from the center? And the answer is that we just need to remember that annoying Euclidean distance formula, which is the distance from the center is equal to d is equal to the square root of x squared plus y squared. Squaring it, by the way, does help us make sure that the negatives don't even matter anymore. That's That's the distance. By the way, this works for any dimension. If it was a 3-dimensional thing, we'd just be doing x squared plus y squared plus z squared. So that's just simply the distance formula for Euclidean space, which is the normal space that we kind of work in. That works for everything except really, really large distances and infinitesimally small distances where the laws of physics break down. or Newtonian laws kind of break down, I should say. Okay, it works really well there. So that's our distance. So that is represented over here. The distance from the center is equal to math dot square root of x squared plus y squared. And then what I do is so there, I generate a point and I figure out it's how far that is from the center, and I say if it's greater than 1, it's a miss, otherwise it's a hit. But to help us visualize it, I gave us a turtle. And I said, turtle, normally you have this square set up, right? That's just an arbitrary number of pixels. That's defined by the number of pixels. The square you set up, I want the coordinate system to be from the bottom left corner is -1, and the top right corner is +1, +1. Don't never really know that. That's what this does, though. It sets it so that basically that the space that the turtle will be drawing on is the blue square. So Bob turtle. We create a turtle called Bob. Bob.tracer. This is 102.25. This is just arbitrary. But what tracer does is that, as this mentions over here, this basically allows us to speed up the drawing process. Bob will put his pen up, and we change his shape into the classic turtle. And now when we toss a dart, what we'll do is that we'll have Bob mark where that goes. By what Bob will do is that he'll go to that spot. If it's a hit, he'll change his color to blue, and he'll stamp where that hit. If it's a miss, he'll change his color to blue and stamp where that miss was. If it was a hit, he'll change his color to red and stamp that. And then here's just the standard kind of thing that I've been doing for this. Hits is equal to 0. Throws, 10,000. If the toss landed in, and if the toss was a hit, increment the hits. And then what I do is I print out, so see how this is the same formula, same format I've been using. If the hits divide by throws, and then I'll print out the hits divide by throws, which I said would approximate pi over 4. That's not really a useful value that I know off the top of my head, so I'll multiply that 4 to get pi. And so what I'll do now is I will shrink this down so that we can see the output in action. Boop. Go ahead and see the output in action. And there we go. The red denotes a hit. The blue denotes wherever we had a miss. And notice that basically Bob drew a circle. I mean, it's not going to be a perfect circle because, of course, I'm drawing the shape with turtles, with turtle stamps. So, of course, it's going to be a bit jagged. But it tells us, hey, pi is 3.12. I mean, we know it's 3.14, but I mean, like, I can only do so many simulations, right? And have it be visualized at the same amount of time. Eventually, I'll just come up against the limit for running. So here, I approximated pi. All right, so what should I do the next couple of days before I let you go? I'm going to go ahead and post this code because the sharing function isn't working. So the next couple of days, and don't leave yet, please, because this is important for me to figure this out with you. Right, the next couple of days, what we've got is that we've got the Monte Carlo, I moved up where we did Monte Carlo, I did it today. And what we'll do what I think will work is that I will give my lecture on Thursday about how to choose a final project, what options are available for you to choose a final project, and just kind of let you brainstorm a bit. Okay? Then, so basically that will be basically you're getting you set up to do the proposal and getting you set up to do GitHub. Okay? To use GitHub. You'll want to use GitHub. On Tuesday, I think what I'll then do is I will do, once I've done that, on Tuesday, let's see what I normally have scheduled then. On Tuesday, on Tuesday, I will go over the tracks with you, and also go over more continue going over Monte Carlo, as well as going over the pig homework. That will be deployed then. So I'll start going over that and how Monte Carlo helps there. And then I think on Thursday, and the plan is next Thursday to be, not this Thursday, but next Thursday, that will be proposal day rather than the 9th. I think if I hold it in the 9th, because I'll be traveling, that will be a disaster. And then also, and I don't want to push it back to the 11th because that only gives you until this time to work on a final project. And I feel like giving you more time, even if it's just spent just letting it simmer in the back, because I know you have a bunch of other classes and you probably won't start working on it until like here, because you'll realize, oh, there's a project progress report due here. Right? It's not anything to be stressed about. Okay, overly stressed about. Again, I will go over like the kind of options and what kind of options are available. When in doubt, for any student that like does not know what to do, my general go-to response is when in doubt, learn make a visual novel in RenP. It's a way to express yourself. It's much more narrative. It allows you to feel like you're actually making something. Or make a game in Pygame, because there's a lot of different tutorials on how to make games in Pygames. I'm big on games. So some of you have already kind of talked to me about different ideas for a final project. But assuming that we'll do proposal day on next Thursday, I will come up with, I will let you know how that will go. Okay? And then, let's see. Yeah, that's it. I'm going to go ahead and send out the practice exam 2 so that you can see what that will look like. All right? Take care.